One of our motivations for developing a mathematical model of the phenomena we're studying is so that we can make predictions. Often there are experiments that are either very difficult to do or even dangerous. Suppose we wanted to know what will happen if a nuclear reactor lost all of its coolant. Well, that's not an experiment we really want to run. So instead, we want to develop models that will let us make predictions of what will happen so that we can do the appropriate engineering. Suppose someone came to you as an expert now on the trajectory of arrows and said, how thick a shield would I need in order to protect myself from an archery attack? Let's see if we can use the measurements that we took in the previous segment and help answer that question.
So how would we use the model in order to make a prediction of the thickness of the shield? And it's nice to use the model because, there are times when experiments are sort of impractical or inadvisable. So standing up with a thin shield and having somebody shoot arrows at you might be a very bad idea because the shield might not do what it should, and somebody says, aha, it needs to be thicker, but it might be too late for the participants in the experiment. So what we want to do is to figure out how to use our model now that we have for the trajectory of an arrow and see if we can deduce the information we need. So we want to know the speed of the arrow as it reaches the target, because a combination of the speed of the arrow and the mass should tell us a little bit about how thick the shield really needs to be. Well, sadly, we didn't measure. Did we measure it? So no, unfortunately, we didn't measure the speed. But can we deduce it from the model? So what we want to do is using the data that we got from curve fitting, can we deduce the speed of the arrow as it reaches the target? So I modified the code a little bit to print out the values for A, B, and C for the parabolic fit. And these are the values that PolyFit gave us back that described the parabola that was able to predict the trajectory so well. And so I've written that out as an equation here that gives us the height above the launch point as a function of the distance. So this is the distance x, and this is the height y here. Okay, so can we deduce the speed of the arrow? So that's our task here. So the first thing I'm going to do is to determine the highest point in the trajectory. So I want to determine the peak value of y. And what I notice is that the peak value of y sort of happens midway through the trajectory from the bow down to the target. And so this guy is at 1080 inches, and so that means that the midpoint here, y peak, so this is going to be y peak here, the midpoint occurs at distance equal to 504 inches, which is exactly halfway between the bow and the target. So I can actually plug that in here. So if I can go use my mathematical model now to compute y peak, and I plugging in x equals 504 and doing the arithmetic, I'm going to end up with y peak being 21 inches, which is 0.53 meters. Okay, so my next step is to figure out the time it takes the arrow to fall from its peak all the way down to the target. So as the arrow is falling here, as the arrow is falling from its peak down to the target, the thing I'll observe is that's completely that the acceleration in that direction is happening completely because of the force of gravity on the arrow. And so time for arrow to fall from y peak down to 0. And so we know from sort of our Newtonian physics that distance equals 1/2 at squared. And using that, I can sort of solve for t, and that's going to be the square root of twice the distance, so twice y peak, and the acceleration due to gravity is g. And so if I go off and do that computation, I discover that t equals 0.326 seconds. So that's the amount of time it takes the arrow to travel from here to here in terms of time. So this time is equal to 0.326 seconds. And the distance I'm traveling is from here to here, which is 504 inches from the midpoint to the target. So let's see. So the speed now, so now we can just quickly do the speed. Okay, and so that's 504 inches. This is the distance in 0.326 seconds. And so if I do a little arithmetic, feet per second. Well, I'm a little nervous about I can compute with lots of precision. I can do the arithmetic to lots and lots of decimal places. It's not clear how accurate that is given the errors in the measurements and stuff. So maybe it would be safer to say it's somewhere around 135 feet per second. And we'll leave it at that. So what we've done here is to show, with a bunch of, once we have a curve-fitted model, we can actually, derive implications of that model and help us with some determine some measurements, predict some measurements that we didn't actually need to go take.
This brings us to the end of our brief glimpse about how to use computation to process and understand our data. If data crunching is in your future, you might want to learn much more about statistics. It's the study of how to correctly process data and learn what it has to tell us. I encourage you to learn more about the statistical tools that are available in PyLab.